Hello, thank you for coming. My name is Justin Wells. I'm an undergraduate student at the University of North Carolina, Wilmington, Department of Earth and Ocean Sciences. Today I'm going to talk to you about mapping hydrologically sensitive environments in alpine forests of the western United States using remote sensing and GIS. National forests are uncommon in the eastern and interior United States, but they cover vast areas west of the Front Range. This past summer, I worked as a field intern with the National Forest Service near the Front Range of the Rocky Mountains. The Front Range from Albuquerque, New Mexico to Fort Collins is one of the fastest growing regions in the interior United States, with a 2010 population of 5.5 million. The largest city, Denver, receives on average only 13 inches of rainfall per year. The Front Range and surrounding area is also a huge agricultural producer. Almost all the fresh water that supports these metropolitan and agricultural areas originates as snowmelts in the mountains to the west. My work with the Forest Service took place in the Medicine Boat National Forest and was part of a nationwide study to inventory, locate, and characterize groundwater-dependent ecosystems in national forests. High elevations in the Medicine Bow National Forest can receive up to 250 inches of annual snowfall on average. In the spring and summer months, this snow melts, penetrates the surface, and seeps into subsurface aquifers. From there, water flows downhill, and where the water table intersects the Earth's surface, it creates a number of surface features, which in this area are dominated by glacier lakes and groundwater-dependent ecosystems. Groundwater-dependent ecosystems, or GDEs, rely on groundwater rather than precipitation for most of their water input. There are many types of GDEs, but fens, springs, and riparian wetlands are the most common in this area. The Medicine Bow National Forest is mostly covered by pine forests, but these small ecosystems are dominated by sedges, moss, willows, and forbs. They occupy small amounts of the forest area, but contribute significantly to its biodiversity. For geospatial classification, ongoing research to inventory these GDEs involves aerial photography, USGS topographic maps, and then site visits to verify the initial identification. It can take research teams hours to reach one site, often to find that it's not groundwater dependent. My research objective was to determine the likely locations of GDEs using geospatial analysis. This research could increase the efficiency of dozens of research teams across the country. I'll briefly outline my workflow and then explain each of the steps in greater detail. My workflow began with a pre-processed Landsat OLI image. I clipped this image to include only my study area, and then used the multispectral image to calculate NDVI and perform a supervised classification using reference sites that I obtained during my fieldwork. I then downloaded a LiDAR-derived digital elevation model. This image was clipped using the same shapefile. I then derived slope and flow accumulation to calculate compound topographic index, or CTI. I also used the DEM to derive geomorphological features using a filter and raster algebra, which I'll explain later in this presentation. These 4 new images were then reclassified with various weights, and then summed to determine a combined likelihood. Chlorophyll in plants creates a distinct spectral profile. Healthy vegetation reflects high in the near infrared and low in the red portion of the spectrum. By taking the sum of these 2 bands divided by their difference, you can differentiate between healthy vegetation, unhealthy vegetation, and non-vegetated areas. The original image was taken after a dry period of the summer months when groundwater-independent vegetation was likely to be stressed due to lack of water. NDVI was then reclassified to reflect relative likelihood of groundwater dependence. The same Landsat image was used for a maximum likelihood classification. I collected reference sites in the field and supplemented those sites with Google Earth imagery and knowledge of the area. In the reclassified image, the GDE was given a value of 3, and other classes were given a value of 0. A compound topographic index, also known as topographic wetness index, is used to model a soil's state of wetness. The first step is to calculate orthogonal flow direction. Each cell is then given a new value reflecting the number of upland cells that flow into it. A higher value of accumulation means wetter soil. This value is used in the numerator of the CTI. Higher slope allows for quicker drainage, which leads to drier soils. So slope is used in the denominator of the CTI. The actual value of CTI is the natural log of upland contributing area over the tangent of slope. GDEs are likely to be found where water accumulates, so in this image, a high CTI value represents high likelihood of groundwater dependence. The image was reclassified with high and low CTI values reflecting high and low likelihood of groundwater dependence. The last layer utilized a raster filter to classify geomorphic features. This image shows a 5x5 cell matrix representing elevation and a cross-section profile. Each cell is filtered using a 3x3 cell filter. The new values reflect the average of the original cell values and the 8 cells surrounding it. The third image shows the difference between the filtered matrix and the original. Notice that the cells around the center now have negative values. We can apply this concept to a profile where the x-axis is distance, the y-axis is elevation, and the black line represents a topographic profile. The blue line is the result of a moving average filter over the original profile. The red line is the calculated difference. Everywhere where the blue line is above the black line, the red line will have a positive value. This highlights areas of high slope relief and negative curvature where the water table is likely to be near the surface. This concept was then applied to a digital elevation model to determine local relative elevation. 4 unique likelihood values were calculated for each cell in the study area. These values were then added together to create a new value for each cell. So for example, if it was given these 4 values for each of the classifications, the new value would be 10. This map illustrates the combined likelihood of groundwater dependence based on the NDVI supervised classification, CTI, and morphology filtering techniques. I'm currently awaiting new material that will allow me to perform an accuracy assessment, but based on the correlation between layers in comparison with my ground truth reference points and knowledge of the area, the model appears to have done a good job determining groundwater dependence. Accuracy assessment is the next step for this research. After that, the model should be tested on other alpine forests in the Rocky Mountains. Radar imagery could be a huge addition, but it's extremely expensive. In other national forests, SUR-C radar imagery is available at no cost. GDEs contribute to the biodiversity of the greater ecosystems. The water that flows through these systems is used for residential, agricultural, and thermoelectric power for the millions of people who live downstream. They are delicate ecosystems that are threatened by several factors, but the primary threat to these ecosystems remains hydrologic diversion, often due to road construction and maintenance. I'd like to thank Dr. Nachisa Procope for her continuous support of my education. Will Abrams, who made it here today, he's been helping me for a long time. And Maria gave me a lot of feedback. She actually made it today too. She gave me some feedback yesterday. Thank you. I'd also like to thank everybody who made this conference possible and everyone in attendance for your time and consideration. And with that, I'll let the credits roll. Any questions?